Okay. We had finished with this problem. No, the log one I was talking about, there's also what's called a logarithmic change you can use. So suppose you want to measure the size of the distance. We used absolute change and relative change. There's also a logarithm one. It's 2.3 times the log and then the new value divided by the original value. Or I had given you a formula yesterday. When you're dividing, you could subtract them. I'm not sure why the book likes this one better. I prefer this. Sometimes what happens here is this 2.3 would have to distribute to both of these. Or you have to subtract the logs first and then multiply by 2.3. But this is expressed in, it's called Neppers. And a lot of the parts we'll see is centneppers. Remember, centi is 100, so it's 1/100th of a nepper. It's the ratio of the new and the old, or original. So original is either your starting point, your old value. You'll see it written a couple references, the other one they use. Let's try it. So we did this problem. We found the absolute change, which was just subtracting them, and that keeps the same units. And then we found this was the soybean problem. The one was genetically modified, and so it got 6 more bushels per acre. Then we found how much it changes by a percent. It's 11.8% more soybeans for the genetically modified one. So almost 12% more. Now to see how that compares to Napers, we would use this formula. So it'd be 2.3 log, and then it's the new value, which the new soybeans were 57 and the original were 51. And just plug it into your calculator. 2.3 times the log 57 divided by 51. Now this is Napers. To make it into centinapers, you would, because it's 1/100th, you'd multiply by 100. So this is similar to the percent. It was 11.8%. But it's not a percent. It's centinapers. Another unit of measure. Any questions? A small relative change in a quantity P percent corresponds to approximately a logarithmic change in P centipers, which is what we found because the soybean, the percent was 11.8%. And this was 11.1 if we use the same units or decimals. So it's a small difference, but they're close. The Earth's current human population is about 7 billion, and its relative increase growth rate is about 1.1% every year. If this trend were to continue, let's figure out the population would be 1,000 years from now. Now we can do it using exponents or logarithms. So we're going to do both and see where it ends up. Using the exponents, you would use this. Now, in some books, they call this a 1+ rule because you're taking 1 plus the rate. Remember, the rate needs to be a decimal. S sub 0 is your starting amount, which they said 7 billion. So 7 billion has 9 zeros. And then we're going to multiply that by 1 plus our rate. Our rate written as a decimal, divide that by 100. Now this is a growth, so it's positive. If it was a decay or a decrease, it would be a negative R. And number of years was 1,000. Now make sure you're plugging these in to make sure that's the biggest mistake that happens, is plugging them in wrong. Now I'm going to round that to 4. So it's approximately 4 times 10 to the 14th. Very large. Thousand, million, billion, trillion, zillion, 400,000, billion, trillion, 400 trillion people. Any questions on that? I'm looking at the log. 1.1 increase each year. The increase is approximately then 1.1 centipers. But for the log formula, you need in napers. So if we have centipers, we need to divide by 100 because so that the centipers cancel, we would have the 100 on the bottom. So we would be dividing by 100.011. That's why we multiply by 1 over 100. Now, using the formula for logs, and we want to find the new amount. We need to know the total number, because it was 11 years, or the number of years, which was 1,000 years. So we know the number of neighbors, but it has to equal the total amount of years. So we multiply that by 1,000. Any questions on that? This is how much it's increasing each time. Each year, 1,000 years, it'd be 11. Any questions? Now you need to solve this equation for new. You could put a variable there, but to do that, the first thing you want to do is get this log by itself. So we'll divide by, because this is multiplied, we'll divide by the 2.3. I'm just going to write billion here for right now instead of having to put all those zeros. Now remember, to get rid of the log, this is a base 10. So we take both sides to the 10th power. When the base and what you're taking it to the power of are the same, you could think of that as canceling. I haven't calculated this because it's probably going to be a decimal. And so I'm going to wait until I have new by itself. If you wanted, you could calculate this and just keep that decimal and keep working with it. To get rid of the 7 billion, we're dividing, so we need to multiply by it. I put my zeros here so then I know how many to put when I plug it in my calculator. When you put this in the exponent, mine doesn't go up. I'll show you two different calculators. If it uses a caret, this has to be in parentheses, or you'll get the wrong answer. Then close the parentheses and multiply by your 7 billion. Which is the same as we got here. Remember, the other one was a little smaller than 4. This one's a little larger than 4, but same approximation. Any questions on that? You positive? Okay. When the first draft of this chapter was being written early October, The Center for Disease Control was reporting the viral disease Ebola was uncontained in West Africa, with the number of cases doubling approximately every 20 days. At that time, the number of known Ebola cases was 8,000. So that's your start. If the virus had continued to spread at the same exponential rate, how long before everyone on Earth would be infected? Using exponential growth, we can plug in S sub 0, that's your starting amount. There was 8,000 cases when this was done. Doubling is a 2. Or if you use 1 plus rate, like this, when something's doubling, it's growing by 100%. Written as a decimal is 1. So 1 plus 1 is 2. So if something doubles, it increases by 100%. Written as a decimal is 1. 1 plus 1 is 2. Any questions on that part? There's a lot of different amounts for the population of the world. If I had it on a test, anywhere between 7 billion, 7.3 billion, somewhere in there is fine. Your book's been using 7 billion. Anyone have a preference?
The smaller one?
The 7?
Yeah.
7 billion. We'll go with that. So we have our 8,000 cases, 2, and then we're looking for this T because we want to know how long. And that would be in days because this is 20 days. Population, we said 7 billion. Now, when you're solving, we're solving for this T that's in the exponent. So we need to get this by itself first. How do we get rid of the 8,000? And if you don't want to say it, type it in the chat.
Multiply.
We are multiplying, so we should do the opposite. So since this is times, we divide. Over here, we were dividing, so we multiply. So always think about, if I plugged it in my calculator, what would I be doing? And I'd be taking 8,000 times this. So to get rid of it, I need to divide. Now, what's nice about a lot of zeros at the end? I could cancel these 3 and these 3, and then I have a little less to type. I know this won't be a long decimal, so I'm going to divide. It might even divide. 1, 2, 3, 1, 2, 3. Yeah, because the 8's a bunch of 2's. Now, if this was a long decimal, I'd either keep that decimal in my calculator or I would have left the fraction. Any questions on that part? So I divided so the 8,000s would cancel. Now my variable's in the exponent. Remember the rule for logs? If the variable's in the exponent, if you take the log, you can bring that variable down. That's what we want to do. So we could take the log of both sides. That means this can come down in front. Any questions so far? This one we're multiplying by that because we want to get t by itself. So let's get this part by itself first. This is multiplied times t over 20. So I'm going to divide it. I'm going to move it over here. The log 2's cancel and we have t over 20 equals any questions so far? Now that 20 is in the denominator. This is t divided by 20. So to get rid of it, we multiply. And then we just plug that in our calculator. Twenty log 8. Now make sure you close this parenthesis before you divide by the other log. $394.778. This was in days because it repeated it doubled every 20 days. So it would be 395 days, a little over a year. Any questions on that? I was looking at this problem this morning and I had typed it out, but then when I was doing it, I think we might have to open the book and look at it, but Harry Potter and Hermione Granger visit the Three Broomsticks in Hogsmeade. Harry orders a hot butterbeer. The initial temperature of the butterbeer is 168. And the ambient temperature of the Three Broomsticks is 56 degrees. So that's the room. Each minute, the temperature of the butterbeer decreases by 0.11. Oh, that's the decreasing. Okay, 0.11. And then this is the butterbeer and the ambiance of the room, where T sub B is the temperature of the butterbeer and T sub A is the ambient of the temperature, which remains constant. Harry Potter can drink the butterbeer only after its temperature is below 119 degrees. How long must Hermione wait for Harry to drink up? So we can use this formula. I was thinking they wanted us to use this for the difference, but we can use this. In an offset exponential model, the difference between the stock value and the set point behaves exponentially. Therefore, we can consider the difference to be T sub B minus T sub A, the initial value for time 0. See, that's the part I don't think is correct, because if we use that, then it would be 168 minus 56, which is 12. It's lower than what we're trying to get to. I think the initial value has to be the 168. It doesn't make sense to start at 112 if you wanted to cool down to 119. So I'm not sure if I missed something in the book, but I think the starting amount needs to be the temperature inside. Because that's what it's starting at. Our rate is negative because it's cooling down. So it's a decay. Negative because this exponential decay model. The temperature of the butterbeer approaches the set point given by the ambient temperature. So we want to know when the starting amount 168 reaches 119. So this is our starting temperature of the beer. It's decreasing by 11% each minute. So X is minutes. Any questions on that part? To get X by itself, we first want to get this by itself. This is being multiplied 168 times the quantity. So to get rid of it, divide. Any questions so far? When you have an X in the exponent, take the log of both sides. Because then that X can come down in front. I'm going to subtract that 1 minus 0.11.
Are we allowed to divide first before we move the log?
Yes. The only thing is if it's a decimal, you need to keep that decimal the whole time. Don't round it. So if we were going to go 119 divided by 168, then you want to take the log of that answer. We're multiplying by this log. To get X by itself, we need to divide by it. Should have kept that answer. But you never want to round until your final answer because things can end up a little different. Well, if it's cooling down by 11%, she only needs to wait 3 minutes. Depending on the cup and how well it insulates. Any questions on that? Show that the log of 0.5 is the same as a negative log of 2. So to show it, because they were saying obviously it's the log of 0.5 is a negative log 2, but I mean, for most students, that's not obvious. I wouldn't expect you to think it was obvious. Now we could start with either side. Probably easier to start with 0.5. So if we start with log of the 0.5, well, notice we need a 2 in there. 0.5 is the same as what fraction? Anyone?
50%.
Yes. And 50%, but we want a fraction.
Oh, half.
Yeah, there we go.
Sorry.
Yeah, nope, that's all right. So 0.5, if you weren't sure, that's in the tenths position. So that's 5/10, which reduces by 5 to 1/2. And 50% of something is half. But the reason I wanted to get the 2 in there is because this has a 2. So 0.5, I thought of the 1/2 to get that 2 in there. Now notice the hint. 1 over x, if we bring it up, it makes the exponent negative. So anytime you have a negative exponent, you could always move it to the denominator, which makes the exponent positive. Well, since this one's in the bottom, we're going to move it up. So this is the same as the log of 2 to the negative 1. And that's why when we're dividing, we subtract the logs, because that bottom part has a negative exponent. Remember, exponents we can bring down like we did here, bring it down in front. So these two are the same thing. But it was just a little exercise showing you this log. I mean, this, in case of negative exponents, in case we run into them more. Any questions on that part? They gave a couple formulas for doubling or half. So this, they say these two are exact. This is an estimate that we can use. If a process is growing exponentially with a rate R, the doubling time is this formula. So if you went to a bank and you found they had 2% interest rate, you could see how long it would take for your money to double. If you put money in there, never touched it, how long it takes to double. Then the decaying one is how long it takes to go in half. And a lot of times they use that for, I think I made a problem for oil. I think it was oil. How long it will take before our oil reserve is cut in half. Anything's decaying. If an area of crops is dying off from a certain type of bug, how long will only half of it be left? So this is seeing when things are cut in half, where this one is doubling. I think it was the Ebola one where the bacteria was doubling every so often. Forget how often it was right now. That would be used for this one. Now this is an estimate for doubling time, and when we do this problem, we'll also use this. But the only thing, your book uses this formula. You need to be careful because you're not using the decimal here. So it's 70 divided by your percent, not your R value. A lot of times, almost always, we use R plugging into a formula as a decimal. This is the decimal. This one is the percent, not the decimal. So this one's a percent, this one's these two are both decimals. Okay, let's try one. If we want to put money into an account at 6.5% and want to see how long it takes to double, use the doubling rule, which should give you the exact amount, and then use the estimate and compare them. So the doubling rule is this one. Log of 2 divided by log 1 plus R. 6.5% written as a decimal. And remove the decimal to the left, 2, divide by 100. And let me just plug that in. One, 2, 11%. No, it's not a percent. It's how long? It'll be years. So at 6.5% in 11 years, the money will have doubled. Any questions on that? Now to try the estimate, you just take 70 and divide by the percent. It was 6.5. And that will tell you the number. So this one is an exact value. This is an estimate. It gets the same value rounding wise. In some books, there's a rule of 70 and a rule of 72, and it splits at 5%. So you use rule of 70 if it's less than 5%. You use 72 if it's greater. Let's see if that gets us closer. Yeah. But your book just shows rule of 70, which is fine. Any questions on that? One fossil fuel is oil, and it's declining by 2.5% per year. How many years before we have depleted half of what is there? Well, that would be this one. It cuts it in half, or it tells you how long it takes to cut in half. So it's the negative log. It's the same thing, only it's a negative because it's a decrease. And in place of R is 2.5%, 0.025. One. Exponentially negative. Because this is decaying, this needs to be negative. It's almost the same answer, but you should be subtracting this. This is a negative because this is a decay. $27.4 years. So 27.5 years, oil will, if it goes at the same rate, we will have half the oil we have. Any questions on that? Okay, some definitions. It says in economics, the term capital refers to assets that are used to generate income. For example, a combine that enables a farmer to harvest wheat more quickly, a bridge that allows goods to follow to the new market, a drug patent that allows a company to make money from a new treatment. The process by which new capital is created is called investments. So capital is your assets, anything that helps you generate income. Investment is when you build those things or invest in them. And the process by which capital wears out or becomes obsolete is depreciation. The bridge gets weak and you need to fix it, it depreciated. Or you could run out. So depreciation is also running out of things. So you have your investment. Now, when the investment, that would be going into the capital stock. That's your stock. When it's going into, the blue ones are those you shouldn't have trouble getting. The blue ones are, if it's going into the stock, it's a plus. This one's coming out, it's a minus. When capital increases, you invest more. So when this increases, that increases. When capital increases, there's more things to depreciate. So if this increases, both of these will increase. It's odd, so it's a stable flow. If you're just looking at this one, this would be, there's no negatives, so it's growing. Where this one's stable. There's what's called the static reserve index. A non-renewable resource is the length of time it will last at the present rate of consumption. So like the reserve of oil, if we keep doing it at the rate we're using it and don't slow down, then static reserve tells you how long it takes at that rate before it's gone. Because this isn't a renewable resource. Oil is not. It's not something we can make. Any questions on that? Okay, so you should be able to do all of the attendance problems. So try all of them. If you have questions, we'll look at those on Wednesday. Any questions?